In this lesson, we will study parametric equations, graphs, and some applications. So we have graphed sets of ordered pairs. We're really familiar on graphing functions like f of x, and we've even graphed polar equations. Now we will study parametric equations. Here's the definition. A plane curve is a set of points x comma y such that x is equal to f of t, y is equal to g of t. So both x and y are defined as functions of t. And f and g are both defined on an interval, let's call it I. These equations, x equal to f of t and y equal to g of t, these are called parametric equations, and t is called your parameter. Check out this first example. Let x equal t squared and y equal 2t plus 3. For t inside this interval from -3 to +3. Graph the set of ordered pairs x comma y. Now please keep in mind that x is defined to be t squared, y is defined to be double t plus 3. What we're going to do is we're going to generate some ordered pairs. We're going to make a table of values for t, x, and y. We're going to choose t values between -3 and 3, and we are going to plug these t values in to generate x and y. Now both your x and your y coordinates are dependent upon what you choose for t. So here's my table of values. We're going to choose a t value, and then we'll generate x and y. So let's start here with t equal to -3. Now remember what x is. X is t squared. So in this case, it'll be -3 squared, which is 9. Y is 2t plus 3. So it'll be 2 times -3, which is -6, plus 3, which is -3. Let's choose now a different value for t. How about -2? Remember that x is t squared. So -2 squared, which will be +4. Remember that y is double your t value, so 2 times -2, which is -4, plus 3, which is -1. Let's continue doing this for different values of t. So I went ahead and plugged in -1 for t, 0, 1, 2, and 3. Now remember, these t values are only defined on this interval between -3 and 3. So you're not allowed to choose any t value that's less than -3. You're not allowed to plug in any t value that's greater than 3. All right? All right, so here are the ordered pairs that you're going to plot. 9, -3, 4, -1, 1, 1, 0, 3, 1, 5, 4, 7, and 9, 9. So as you plot the points and draw the plane curve through the plotted points, you can see that it is a portion of a parabola that is opening sideways. Now, listen, this is just a portion of a parabola because this graph here ends at this point, and it ends at this point. Please be very careful to not continue the graph with an arrow here or with an arrow over here. Remember that this plane curve is only defined for t values between -3 and 3. So we have to make sure that this point here, the graph ends right here. Do not do the following. Here, let me show you. Don't do this. That would be wrong. This would be wrong down here too. To draw arrowheads on the both ends of the parabola, it does not continue. So it's only defined on this interval. Now these are not x values, these are t values. So the parabola is only defined from when t is -3. And remember, when t is -3, you're at this point, 9, -3. You're right here. It's only defined from here all the way till when t is 3. And when t is 3, you're at the point 9, 9. So this point. So it's defined from here all the way this way. Matter of fact, let us draw arrows showing the direction that the curve traces as t increases. As t values increase, the curve traces the graph, the curve traces this pattern here, or this curve. All right? So these arrows here indicate the direction that the curve traces, as t values increase. Pretty cool, isn't it? What you can do here, because we have parametric equations, is if t stands for time, you can now say, okay, where are you on this plane curve at 2 seconds? At time equal 2 seconds, you're at the point 47. You're at this location on the curve. So now I can figure out where I am, what location I am along this curve given time, right? In seconds or minutes, whatever it is. Okay? Cool, let's look at another one. Now, example 2, find a rectangular equation for the plane curve that we just finished graphing. Let me remind you of what the parametric equations are for example 1. X is equal to t squared and y is equal to 2t plus 3. What you and I want to get is a rectangular equation, so an equation that you and I are familiar with, right? That it represents that parabola that was opening sideways. So this is the thought process. We want to eliminate t, eliminate the parameter t. So what you want to do is choose one of these equations to solve for t. Solve either one of these equations for t. Now, it's recommended that you solve this equation for t as opposed to this equation for t. Because, let me show you, if you choose to solve this equation here for t, what you're going to end up doing is taking the square root of both sides, right? Remember, you want to isolate t. So you would get t is equal to, watch this, plus or minus the square root of x. The problem with this is that you have two options or two values for t, either positive root x or negative root x. And we would rather have a unique solution for t, a unique solution for t. So notice that if we solve this equation over here for t, you will get the following. T is equal to y minus 3 over 2. There are no two solutions for t over here. It's just, there's only one solution. It's unique. T is y minus 3 over 2. You get a unique solution as opposed to over here, you don't get a unique solution. You get t is either positive root x or it could be negative root x. So we're going to get rid of this. We don't like solving this equation for t because you don't get a unique solution. All right, what we're going to do now, you could probably sense what's coming. We're going to take this t value and we're going to plug it into the other parametric equation. Okay, so let me see if I can split this here. All right, so now what I will do is I will come over here where it says x is equal to t squared, but now I know that t is y minus 3 over 2 quantity squared. You see what I did there? T is equivalent to y minus 3 over 2. So I'm going to take that value and plug it into the other equation. And now I will solve, or I will basically simplify and rewrite this equation so that it looks like a familiar rectangular equation for that parabola. Can you notice that this equation now no longer has t in it? This equation only has x and y. All right, so let's do it. So let's simplify this a little bit. So you got x is equal to y minus 3 quantity squared over 2 squared, which is 4, right? So what we can do here is multiply both sides by 4. And let me move this up a little bit. All right, so what you can do is multiply both sides by 4, and you get 4x is equal to y minus 3 quantity squared, right? So that's the same thing as saying y minus 3 quantity squared is equal to 4x, right? If you want to, and that's good right there, or if you want, you can, let me actually box that before I move forward. So this is a good, that's a rectangular equation for that parabola opening sideways. And this looks awfully familiar, right? When you study conics, you study that when only one variable is being squared, in this case only y is being squared, then you have a parabola. When y is being squared, you know the parabola opens sideways. And when the coefficient of x over here is positive, you know the parabola is opening to the right. So you know that this equation looks very familiar. This is a rectangular equation for a parabola opening to the right. Now, if you want, you can expand this, right? If you wanted to, you could expand the left-hand side to be y squared minus 6x plus 9 is equal to 4x, right? And so you could rewrite this as y squared minus 4x, if you brought that over to the other side, minus 6. Excuse me, this should be a y, shouldn't it, everybody? Can we fix that really quickly? This right there. All right, very good. Let's go back. Y squared minus 4x minus 6y plus 9, and all of this is equal to 0. This is an equivalent equation, rectangular equation, for that parabola that is opening to the right. Notice that there's only one variable being squared, and that's y, so I do know that this is an equation for a parabola opening sideways. So I'll put a big word or here. So either one of these equations could be written as a final answer, a rectangular equation for that parabola, okay? And actually what we could do, actually this might be the best way to write it. What we could do, so I guess another word or here, you see this equation here, if you divide both sides by 4, you will isolate x. If you divide both sides by 4, you'll get x is equal to 1/4 times y minus 3 quantity squared. That might be my favorite form that this equation is written in. But I do want to call something to your attention. This equation is for that parabola that is opening to the right, but we need a restriction on your x values. Let me show you the picture once again. If I can scroll up. Notice that this parabola is only defined for x values from, let's see, 0 to 9. 0 to 9. I mean, if you can look at the picture, you can look at the graph, or you can even look at the table, right? The smallest x value here is 0, and the greatest is 9. The graph is only defined for x values from 0 all the way to 9, right? From 0 to 9. So what I want to say over here, I want to say that this is my final answer here, but I want to be very careful about my restriction on my x values. So I'm going to say 4, right? I'm going to say 4x in this interval from 0 to 9. If you don't give the restricted domain, then we're going to have a parabola that goes on forever to the right. And you and I know that it doesn't. It stops, right? So this restriction is very important. All right, let's graph a new plane curve. Now, this plane curve is defined by these two parametric equations, okay? Remember, t is called your parameter, and each one of these equations, x equal to 4 cosine t, y equal to 2 sine t, each one of them are called parametric equations. Now, this curve is defined for t values inside this interval from 0 to 2 pi, from 0 to 2 pi. Now, in the first example, what we did is we solved one of the equations for t. Now, that is not going to be productive here. So instead, we're going to use a fact. We're going to use that this fact. You remember sine squared of t plus cosine squared of t is equal to 1. You remember that Pythagorean identity? We're going to use that here. So what I want to do is I want to take this parametric equation, and in order to take advantage of this Pythagorean identity, I'm going to need to square cosine. So what I want to do is square both sides. So I'm going to have x squared, I'm squaring both sides, is equal to 16 cosine squared of t. What I'll do is I'll isolate cosine squared of t, okay, everybody? So follow me here. So I'm going to have x squared over 16 is equal to cosine squared of t. Now, let's not lose the other parametric equation. Let me come over here. The other parametric equation is y equal to 2 sine t. What I want to do is square both sides so that I can use my Pythagorean identity. So I get y squared is equal to 4 times sine squared of t. That's the same as y squared over 4 is equal to sine squared of t. Now, I want to use this fact that if I take sine squared of t and add cosine squared of t, I'll get 1. So what I'm going to do is I'm going to take sine squared of t, which is y squared over 4, add it to x squared over 16, and I'll set it equal to 1. Okay? So here we go. I'll have sine squared of t, right, plus cosine squared of t is equal to 1. That's the Pythagorean identity. And now with my substitution, I have y squared. I guess I should move down, huh? With my substitution, I have y squared over 4 plus x squared over 16 is equal to 1. This is the equation for an ellipse. Let me rewrite this just a little bit. You know addition is commutative, so I'm going to write this as x squared over 16 plus y squared over 4 is equal to 1. This is a very familiar, I hope it is, a very familiar rectangular equation for a horizontal ellipse. We know it's a horizontal ellipse because the larger denominator is underneath the x term. And we know that the center is h comma k or 0 comma 0 in this case. Okay, so let's go ahead and graph this ellipse. So we know the center is the origin, and I have to move, because it's a horizontal ellipse, I want to move left and to the right of the center, square root of 16 units. Square root of 16 is 4. So I want to move 4 units to the left and 4 units to the right of the center. This will give me the location of my vertices. Each one of these points are called a vertex. And then I want to move up and down from my center square root of 4 units. Square root of 4 is 2. So I want to go up and down 2 units. And these are the location of the co-vertices. And so here's my ellipse. Very famous shape there. So there's my ellipse centered at the origin. That was a lot of fun. And it uses this equation. I love that the parametric equations use that Pythagorean identity. Good job. All right, I think it'll be worth our time to look at another example like the one we just did. Okay, it's very similar. Here we have a pair of parametric equations. X is equal to 2 sine t, y is equal to 3 cosine t, and t is defined from 0 to 2 pi. What would be really great is if you pause this lesson right here, pause the video, and try this example on your own, and then I'll check in with you in just a minute. So go ahead and pause the video here, give this one a shot. Okay, I went ahead and squared each one of my parametric equations, and then I isolated both sine squared of t, this should be sine squared of t there, and cosine squared of t. All right, using our Pythagorean identity, sine squared of t plus cosine squared of t is equal to 1, I get the rectangular equation x squared over 4 plus y squared over 9 is equal to 1. Now we know this time around this will be a vertical ellipse, and that's because the larger denominator is underneath the y term. All right, so I'll go ahead and draw my axes now. Okay. We also know that, again, the center is at the origin. All right, I'm scaling my x-axis, scaling my y-axis. All right. Okay, so I'm going to go ahead and plot down the center. Now, in order to find my vertices, I need to go up and down square root of 9 units. Square root of 9 is 3, so let's go up and down 3 units. All right, those are your vertices. And then let's move to the left and to the right of the center. Square root of 4 units. Square root of 4 is 2, so we're going to go to the left 2 and to the right 2. And then we can draw our ellipse, our vertical ellipse. When we say a vertical ellipse, remember that means that the major axis is vertical. The major axis is vertical, and this axis of the ellipse is minor. That's the minor axis. So the major axis is vertical, the minor axis is horizontal. So here's the ellipse. Excuse my sloppy drawing. Cool deal. I hope you did well. All right, before we look at a really great application, let me give you some information. Parametric equations are used to simulate motion. If an object is thrown with a velocity of v feet per second at an angle theta with the horizontal, then its flight can be modeled by these two equations. X is equal to v times cosine of theta times t, and y is equal to v times sine of theta times t minus 16t squared plus h, where t is in seconds and h is the object's initial height in feet above the ground. Here, x gives the horizontal position information and y gives the vertical position information. The term negative 16t squared occurs because gravity is pulling downward, and these equations ignore air resistance. So we're going to use these two parametric equations when we are dealing with an application that is simulating motion. All right, here we go. All right, Jack launches a small rocket from a table that is 3.36 feet above the ground. Its initial velocity is 64 feet per second, and it is launched at an angle of 30 degrees with respect to the ground. There's a lot of information we need to find. First, find the rectangular equation that models its path. What type of path does the rocket follow? And then determine the total flight time and the horizontal distance traveled by the rocket. Okay, let's grab those parametric equations that we were just introduced to whenever something is simulating motion. All right, let's do it. All right, now plugging in the given information, we know that x is equal to, now the initial velocity is 64 feet per second, so I plug in 64 for v, and cosine of theta. Now theta is the angle 30 degrees in this problem. So let's put in 30 degrees. All right, and then times t, which we don't know yet. And then over here we have y is equal to 64 times sine of 30 degrees times t. And let's see if we can squeeze down, bringing down negative 16t squared plus h. Okay, and I also plugged in 3.36 for the h value, which is the initial height above the ground, okay? So 3.36 for that. What we're going to do now is simplify for x. So we have 64 times root 3 over 2, that's cosine of 30 degrees, times t. And over here, we have y is equal to 64 times 1/2, that's sine of 30 degrees, times t, minus 16t squared plus 3.36. Now, let's continue to simplify. X is 32 times root 3 t, and y is 32t minus 16t squared plus 3.36. Now, our first job is to find, find the rectangular equation, right? The way we did this in an earlier example was we choose one of these equations to solve for t. Solve one of these equations for t. I think you would agree with me that this equation here would be a lot easier to solve for t. So let's go ahead and do that now. Let's solve this equation for t. All right, I went ahead and divided both sides of this equation by 32 root 3. So t is x divided by 32 root 3. And for this equation, I just wrote it in descending power order in terms of t. So I put negative 16t squared first, and then plus 32t plus 3.36. Now, just like we did in an earlier example, what I will do now is I will take this value for t and plug it into this parametric equation. Remember, we have a pair of parametric equations here. We took this parametric equation, solved for t, and now we will plug that into this other parametric equation. So wherever you see t, I will replace each of these t values with this expression. All right, I went ahead and plugged in those t values into this other parametric equation. And notice that, I know it looks maybe a little complicated, but look at the equation. It's all in terms of x and y. All in terms of x and y, no more parameter t. Now let's simplify this equation. So we get, let's see, negative 16x squared over, we need to square 32, and 32 squared is 1,024. And of course, when we square the square root of 3, that's just 3. And let's see, what do we have over here? Well, these 32s here divide out. That's good. And so what we have here is just plus x over root 3, like that, plus 3.36. Now let's clean this up even more. So now we have y is equal to, let's see, negative 1 over 192 is what that simplifies to, times x squared, plus, and then if we rationalize this, we get root 3 over 3x, and then plus 3.36. This is a rectangular equation that models the path, right? So for this rocket. So what kind of, this is the answer for the first part, right? For the rectangular equation that models its path. The next question in the problem says, what type of path does the rocket follow? Well, notice that there's only one variable being squared, and that is variable x. Variable x. So that means this path is a parabola. It's a parabola, and because x is being squared, the parabola will open upward or downward. Because the leading coefficient is negative, we do know that this is a parabola opening downward, which makes sense, right, everybody? If the rocket is being launched upward, like this, the rocket does this kind of that kind of motion, right? It's launched up and then eventually it comes down. So it does make sense that the path that the rocket follows is a downward opening parabola. So very formally, I wrote that this equation defines a parabola and the rocket follows a parabolic path. Now, the last question that we want to find, or the last two equations, questions we want to answer are the total flight time, okay, the total flight time, and the horizontal distance traveled by the rocket. Now, to determine the total flight time, notice that they said find the flight time. That means they want to find the total number of seconds, I believe we're talking about seconds here, that the rocket is in the air before it hits the ground, right? So I want you to remember that this second parametric equation, y is equal to negative 16t squared plus 32t plus 3.36. Remember that second parametric equation? Do you remember that y gives us the vertical position of the rocket at time t? So what we really need is we need to set this equation equal to 0 and solve for t. Because if y is 0, then we're talking about the rocket at ground level. Remember, the y variable represents the vertical position of the rocket. So if we want the total flight time, we need to determine the positive value for t, for which y equal to 0 corresponds to the rocket at ground level. okay? With a rocket, when it hits the ground, you're talking about y equal to 0. So what we need to do here is solve for t. You can use the quadratic formula here. Okay, using the quadratic formula gives us that either t is negative 0.1 or 2.1. Now remember, t is in terms of seconds. It makes no sense for the rocket to be in the air for a total of negative 0.1 seconds. That doesn't make any sense in this context. And so the only acceptable answer is 2.1 seconds. That's the total flight time for this rocket. Now, the last thing they asked us to find was the horizontal distance that the rocket traveled. Now, do you remember that this is the equation, the parametric equation that gives us the horizontal position? Remember that from earlier? So this was the parametric equation that gives us the horizontal position. Now what we can do is, if we want to find the total horizontal distance that the rocket traveled, what we can do is plug in our t value of 2.1, right? Plug in that, because this is the total flight time. And so multiply all this together and it'll give you the total distance, the horizontal distance that this rocket traveled. And this gives us about 116.4 feet, right? Feet. This is the total horizontal distance that the rocket traveled. So if you want to picture the rocket, actually, let me draw it down here for us. Let me see if I can draw a picture for us. All right, here it is. So this the rocket. Remember, the rocket was not launched from the ground. If you remember, the rocket was launched from a table that was 3.36 feet above the ground. So I guess I can add that detail here. So I guess here's the table that is 3.36 feet above the ground. But anyway, this is where the rocket started. It went in a parabolic curve. The total time that it was in the air before it hit the ground was 2.1 seconds. And the total horizontal distance that the rocket traveled was 116.4 feet. Wasn't that the funnest example? I hope you enjoyed this, this application. All right. This is the end of this lesson, and I hope you enjoyed it. Catch you later.